So keep in mind that the last homework for this class is due tonight. So please do this last homework. After you do the homework, so after you do your last homework, I can go through and drop the 2 lowest homeworks. So sometime tomorrow, whenever I get around to dropping those 2, expect your grade to go up a little bit. If that is, especially if you have 2 bad homework grades that are messing up your grade. Additionally, the corresponding quiz for all of the hypothesis testing is due Friday. Again, after everyone does their quiz on Friday, expect me to go through Saturday and drop the 2 lowest quizzes for everyone. And so that should really boost some of your grades because there's less quizzes. So moving 2 of 8 quizzes, the 2 lowest quizzes, that's going to bump your grade a lot more, especially for some of you, again, who might have had 2 low quiz grade scores. And besides for that, I do have a final exam practice test on my math lab. You're welcome to attempt it anytime. We're going to go through the not shuffled version, but I know some people like shuffled, some people like not shuffled. So it's up to you which one you want to do. But just keep in mind these last 2 assignments for this class. Additionally, let me go back to talking more about the test. So as I mentioned, you should be able to complete it in 80 minutes. I'll write it like that. If not, you have the whole 2-hour time frame to remind myself when our test is. So our time is scheduled for Thursday, May 13th at, 8 to 10 a.m. This is a test that's going to be in this classroom, not in the library like it was before. There's no room for us over there. So we're taking it in the classroom, and there are enough seats to accommodate everybody. So everybody needs to come to class on May 13th at 8 a.m. to take this test. And again, there's a 2-hour window that we have reserved. So you're welcome to use the whole 2 hours, or you can not have to utilize the whole time. Again, I'm not writing it to that extent. I'm honestly wishing I would have made the final exam today, but I'll figure that out next semester. Additionally, I have no idea how many questions are going to be on it. I do know that, as I mentioned, it's not a cumulative test. So everything after exam 2, so everything chapter 8, 9, and 10 related is going to be on the test. So it's everything regarding distributions, estimation, and hypothesis testing. So all of that's going to be on the test. And again, it's a paper and pencil test. You're welcome to bring a flashcard yet again, which means probably your primary responsibility, realistically, as I look through these notes here, I mean, there are formulas here that you do need to know. But you need to know in which situations do you use certain formulas, and you need to remember all these calculator commands that we've learned. So we've learned several calculator commands, and as you search through here, such as finding inverse normal probabilities, or using the normal CDF function, all of these are fair game on this test. I'm not really going to deviate much from what we've seen in the notes and in the homeworks and quizzes, so keep those in mind. So make sure you have a good understanding of when to use those in what situations. That will really distinguish from getting a good grade versus a bad grade on each corresponding problem. Additionally, let's see, I was just thinking of something. Additionally, I forgot. I don't think of what else might be helpful in this one. But yeah, so you get the flashcard again. Make sure you know when to use what in certain situations. I guess I do also want to mention that all of the tables I'm going to provide myself. So all of the tables that are worth needing, which primarily are going to come down to the T distribution table. That's going to be on there. I don't anticipate we're going to need any preceding table.
So we're not going to do the appendix?
I mean,
Isn't there two different ones?
I think the only thing that I could really ask about is concerning the t-distributions, because remember with all the z-score stuff, we switched to using the inverse norm in the calculator, or just the the normal CDF commands. So basically, we took this whole table and fed it to the calculator. So that means this table is useless in this unit, which is good. I don't have to use this. Whatever information from this table you would need, I would probably just give it to you in the statement of a problem. So yeah, really, this will be the only table that you would need for the test. So I'll provide that. Besides for that, I think that was the thing I was forgetting. Besides for that, we could go through the final exam practice test, or I could just state all the things you need to know. So I actually did get feedback that some people like one way and some people like the other way. So I could just start going through the final exam practice test, or I could just do problems from the practice test until we run out of time. I was thinking about doing the latter. Unless anyone has any objections to that, I'll go ahead and do exactly that. And I will additionally be going through the unshuffled version, so I can go through this chronologically. So let me set my notes to be at the very beginning of this unit. We go through these problems. So let's open up the final exam practice test for the last day of class. Okay. So the first problem is indicative of, well, if you keep attempting the practice test, keep opening it up, there's a few varieties of different multiple choice or definition-based problems, as I've had for the previous two tests. Expect problems to be on there that are multiple choice that you don't have to provide any scratch work for. And with that, so not having to provide any scratch work, that's always nice, but it's either you know it or you don't. So expect about a certain percentage of your test to be like these. And so if you keep going through, keep opening the test, then you'll see the variety of multiple choice that I could ask. So there's something that represents the expected proportion of intervals that will contain the parameter. A large number of different samples, size n, is obtained. We look at our options. Well, the proportion of intervals, well, sounds like either the confidence interval, definitely not the margin of error, critical value, well, it's not the critical value. Level of confidence just says the, well, that could also be it, the proportion of intervals. And so we can always just look and see where that occurs in the notes. Before I start talking about that. And I did clump kind of all these definitions together. And so as we can see here, the level of confidence is the expected proportion. So it's the level of confidence. And we can see that the correct notation here, say right here, 1 minus alpha times 100%. Just like that. So again, you can expect a few multiple choice problems on there, such as what a type 1 error refers to. That'd be a good question. Might be a few other little things on there. Again, if you keep attempting the practice test, you'll see a wide variety of different things I could ask. All right, we'll keep going. And this is really where we'll be starting from the beginning of this unit. So let's go ahead and go there. We'll go through this chronologically. And so this says find, hopefully you remember this notation. This is the mean of the sample means and the standard deviation of the sample means. And you might recognize that notation actually from page 69 of the notes. And you can see the two formulas here and here. It tells you exactly how to find the mean of the sample means and the standard deviation. So we can apply that exactly here. The mean of the sample means is just the mean itself, which is 75. So that one's really easy. The standard deviation of the sample means, well, the formula, as we saw on that page, was the population standard deviation divided by the square root of n. Again, you need to recognize these notations here. By seeing those notations, that should tell you exactly what formula to use. And so sigma, of course, is 36, n is 81, so that's 36 divided by 9, and that's 4. 75, and pretty simple, just like that. So from here, let's go ahead and move on. So it starts to get a little bit more technical with this word problem here. So they tell us the mean time is 16.1 and the standard deviation is 3.8. And they tell us that the shape of the distribution is unknown. So this was part of one of the conditions required to, well, some of these conditions regarding do we have normality? And we were using the central limit theorem and some other conceptual ideas to think about, well, are these distributions in fact normal? And so that's something we can test here. So the sample size needs to be less than or equal to 30. That number 30 is coming up. And so it says that we may need a particular number of samples. So notice in the central limit theorem, needs to be greater than or equal to 30. So this is a condition that we need. It needs to be greater than or equal to 30. And that's why I'm selecting answer choice D. So this is a requirement from that section. So that's something you might need to know. And so what's the probability that a random sample of 35 results in a sample mean time less than 15 minutes? So as we scroll through, this is regarding the probability regarding the distribution of these sample means. Oops. And so what we did here is we needed to, and as we can see in the notes here, we used the normal CDF command. So we used the normal CDF command. And so from this, you can go ahead and determine quite a few things here, actually. So I'm using normal CDF because I'm seeing the word probability, which is normally when normal CDF comes up. It gives us a probability. In fact, it simplifies the whole z-score table for us. Now, with the normal CDF command, what we need is a lower bound, an upper bound. In fact, that's mentioned in the notes here. In fact, it might be a little bit difficult to see. You need a lower bound, an upper bound, the mean, and the standard deviation. And so the lower and upper bound are based off of an inequality. Notice it says less than 15 minutes, which is x is less than 15. If you remember from the notes, when we have a less than sign, this is when we used negative 10,000 by default for a lower bound. So thinking back quite a few weeks ago to when we talked about this stuff. So negative 10,000 will represent the lower. 15 would represent the upper. And then we need to provide the mean and the standard deviation. So from here, we also need to provide the mean and the standard deviation, but they gave us a sample size of 35. So the sample size of 35 means that we're actually giving the mean and the standard deviation of the sample means. So the mean and the standard deviations of the sample means. So we actually need to find that the sample mean, well, that's equal to the mean, which was given to be 16.1. So 16.1. And additionally, the standard deviation of these sample means is just the standard deviation over the square root of n. 3.8 divided by the square root of 35. .8 divided by the square root of 0.6423, just about. And so that's exactly what we put into the calculator. So notice our main goal is to figure out how to set up the parameters of this, or the inputs for this command. Negative 10,000, 15, 16.1, 0.6423. This one's about 4 decimal places, so 0.0434. 0.0434. I'm going to leave it here because I'm not going to ask a problem like part C. I believe I did a similar problem in the notes for part C, but again, I'm not going to really ask it. This would be more typical. So I suppose I'll go ahead and move on to the next problem. Okay, so they tell us the size of the population is 20,000. They tell us n, which is the sample size, and they tell us that the proportion, this is the population proportion, is 0.2. So we are moving on to proportion and P with the hat on top. This is something you need to know. That's the point estimate. That's a fair question I can ask as a multiple choice. So we're going down to section 8.2 now. And with that, they first ask, what best describes the shape of the sampling distribution? And they have a few options here. Now, when I look on the notes, one thing I see about the shape is if these two conditions hold, then we get approximate normality, approximately normal shape. So I'm seeing this one here and this one here. I believe I saw two answer choices that resembled that. And actually, it looks like it's part A. Right here and right here. From here, it wants us to determine just simply the mean and the standard deviation of the point estimate. And we see that those formulas are provided very generously here and here. So start off with the mean of the point estimate, the distribution of the point estimates. Again, is just the, as you see here, the population proportion. So that one's pretty easy. It just carries over. The other one is a little bit more engaged. Standard deviation of the distribution of the proportions. Square root of P, 1 minus P over N. So P here is 0.2, 1 minus 0.2, divided by N, which is 700. And so we can plug all of this directly into the calculator. And we get the standard deviation of the standard deviation of the proportions. They want 3 decimal places. So that's a pretty standard, it's a pretty standard proportion problem, determining the mean and the standard deviation of the proportion distribution. Okay, let's move on. Now we have this problem here where should be a familiar problem. They give us a proportion of 0.74, and then they go out and obtain a random sample of 100 people. And then they first ask us in part A, is the random sample of 100 people, is the way this is asked, is this qualitative or quantitative? Are you satisfied with the way things are going in your life? Well, they can either answer yes or no. So yes or no is more of a qualitative aspect. is going to be qualitative. And it's simply part B. It's just more definition based. It's either yes or no, which is categorical. So if anything, they're just asking, do we understand qualitative versus quantitative? And so now they ask to take this and explain why the point estimate is a random variable. And if we look through these points, this is vary from sample to sample. This is represent a random person included. Variability is due to the fact that different people feel differently. So far, it seems like C. Primarily because this last sentence here, that doesn't really have to do with random variability. So I'm thinking it's answer choice B. Or C, rather. Actually, no, B. I'm sorry. Random person. I believe it's B. That one may be up for contention, but again, that part's not as important. Mainly, it's can you figure out the criteria and the numbers that correspond with this. So we first ask, well, does this satisfy the criteria? Since the sample size is something no more or no less than 5% of the population size, well, we do notice, in fact, I already have it highlighted here in blue, that is one of the criteria for determining that the shape is normally distributed. And so if we look at, or as I mentioned in class, we're going to assume that this is no more. So again, that's not something I'm going to ask on the test. This might be something I ask on the test more so to verify that this condition is true. The random sample of 100 people. And the provided proportion that they gave us was 0.74, 1 minus 0.74. Minus 0.7. So since the two conditions are satisfied, then we get approximate normality by the definition. And then they want us to figure out what the mean and the standard deviation of the proportion distributions are. And so we just need to remember what the formulas are. The mean of the proportions is simply just the mean, or not the mean, I'm sorry, it's the proportion. It's the population proportion, which they gave us to be 0.74. Standard deviation, P1 minus P N. Proportion is 0.74 times 1 minus 0.74 divided by N, which was given as 100. And this is simply a calculator problem. round to 3 decimal places. 0.044. And so that's how you figure out the mean and the standard deviation of the distribution of the proportions, as indicated in section 8.2 here. So as we scroll down a little bit more, and then they ask, what is the probability that this exceeds 0.76? So that gives us an inequality and with this inequality, we can already consider the probability, where the probability corresponds to the normal CDF, because again, we already determined that the data here is approximately normal, which means we're allowed to use this calculator command. Now the inequality we have is greater than 0.76. 0.76, and then the upper bound, we need to trick the calculator. I normally use 10,000. And I mentioned this in the previous section. And then they want the mean that we found and the standard deviation. We get that the probability is 0.32. They want 4 decimal places, 47. So that'll be the probability. So using the distribution from part C, so part C being everything up here, they ask us, would it be unusual for out of 100 people that 66 or fewer are satisfied with their lives? So 66 or fewer gives us a new inequality. Gives us less than or equal to 66, which corresponds with the phrase or fewer, 66 or fewer, which means we use the normal CDF again. The lower bound, because this inequality is less than, use negative 10,000. The upper bound would be 66. The mean and the standard deviation is 0.74 and 0.044, which we found in part C. So notice there's a problem here. So getting 1 is a very unusual answer because we're not actually using 66. Getting 1 is a very strange outcome because this isn't actually true here. 66 is not a proportion. 66 is a frequency. So really what's actually going on here, this is less than or equal to 66 out of the 100 total people. So really what we're asking or providing is 0.66. So notice how inputting a wrong answer, like I did, yields something odd, which gives us some indication that we need an actual proportion. So notice I changed that to 0.66. And now let's go ahead and figure out the normal CDF, but instead of 6.6, I'm going to put a decimal in front. Now we get something that seems more reasonable. 0.345. So the probability is 0.0345. Is unusual because that is less than 5%. 0.0345 corresponds to 3.45%, which is less than 5. Anything less than 5% is considered unusual. So that's how we would handle a problem like that. All right, let's move on. I know on the quiz, a few people asked about this question. On the quiz corresponding to chapters 8 and 9. So let's go ahead and talk about this one. So it really works out fairly nicely. They say something about they sample 25 people, which tells us n is 25. And what they're actually doing is they're actually giving us the point estimate here. They're giving us the proportion. So what we are doing is kind of working backwards a little bit, because we're trying to figure out how many people does this person need to, I guess, ultimately interview, so that way he gets approximate normality. So this NP times 1 minus P greater than or equal to 10 is what we are utilizing here. So if anything, we need N times P, 1 minus P, to be greater than or equal to 10. So if you interview 25 people, like this person did, 25 times the 15%, such as in part A, 1 minus 0.15. If we do this computation, notice it's not large enough. It's not large enough. So that means you need to interview more people. So how many more people? Well, you know that you need 15%. So really, we can use a little bit of algebra here. We know that the population is 0.15. And if we need this inequality to be true, we can use a little bit of algebra to quickly solve for n and figure out what that needs to be. So 15 or 0.15 times 1 minus 0.15, 0.1275 is greater than or equal to 10. To solve for n, we just have to divide both sides. So n needs to be greater than or equal to 10 divided by 0.1275. (78.43-ish). Or in other words, n needs to be at least 79, because n is the number of people. People is a whole number. So you might think, all right, 79, that's the final answer then. Well, the way they worded it, 79 is not quite the answer. They're saying how many more people from the 25 people. You interviewed 25 people, how many more people do you have to interview? That would be 79 minus 25. $54. So 54 more people. This is because of the way they worded it. And if it were asking for 20% like it does in part B, it's the same problem. But every place you see 0.15, you put 0.2. So that would be 0.2 divided by, or 0.2 times, well, it ends up being 0.8, 0.16. That's 62.5. Or in other words, n should be at least 63. So you would need to interview 38 more people. So this one is basically working backwards to maintain the appropriate sample size. This is something that statisticians normally do if they do have a suspected or conjectured proportion. They can work backwards to see how many people should I sample so I can get an approximately normal distribution, guaranteed. But what's the least number of people I can interview so I don't have to waste all this time going out and talking to people? Move on to the next one. All right, so we're moving on to a level of confidence intervals. That means we're done with A2. We're moving on to chapter 9. So with chapter 9 here, again, this is, we mentioned this is talking about level of confidence and confidence intervals and constructing those lower and upper bounds. So here it starts off fairly simply. They want a confidence interval. So construct a confidence interval for the population proportion, because that's section 9.1 is confidence intervals for population proportion. And so what we need to do, well, normally we construct a confidence interval around a point estimate. And just to remember that reason of thinking, the point estimate plus or minus the margin of error is ultimately, this is ultimately the confidence interval. And we know exactly how to construct the error. We scroll down a little bit more. The margin of error is given here. And if you remember from my notes, you should have it written in your notes because I remember writing it. The z-score, or the z-score that corresponds to an area to the right of alpha over 2, that was when we did the inverse norm of 1 minus alpha over 2. So I had this written before. I'll write it again just as a reminder. Again, that's rewriting the z-score, so we're making the z-score table irrelevant at this point. So in order to use that formula, over here we need alpha we need p hat, and we need n. So we need alpha, we need p hat, we need n. If anything, n, they already gave us. So n is easy. That one they already gave us. Alpha is also something we can figure out. 1 minus the proportion of the confidence, the level of confidence, which is 98%. I write 0.98 because I'm writing the percentage, the confidence as a proportion. So that's 0.02. So that's alpha. And then p hat is x divided by n. It's just the proportion. 860 divided by 1100, which we can determine right fast. It's about 0.7818. So once we have all of these things, we can determine the error term, which is, as I mentioned, the inverse norm of 1 minus alpha over 2, square root of p hat, 1 minus p hat, divided by n. Let me make sure that's correct. Yes. And so we have everything. Alpha, we said, was 0.02. P hat is 0.7818. 1 minus 0.7818 divided by 1100. And so remember, the inverse norm in the calculator, we can find that by clicking on second and bars. Again, this is in the notes. For the distribution menu, and we see inverse norm is right here. Now we talked about what may show up on your calculator screen. It's going to ask for the area, the mean, and the standard deviation. For your area, you have to type in exactly 1 minus 0.02 divided by 2. That would be your area. 1 minus 0.02 divided by 2 would be your area. So I know we talked about this before. And then your mean should be 1. No, your mean should be 0 and your standard deviation should be 1. And that should be default in your calculator. If it's not, make sure your mean is 0 and your standard deviation is 1. Or if you have my calculator, if you do just this, it means the same thing. Times, we need a square root, 0.7818 times parentheses 1 minus 0.7818 close divided by 1100. Close one more time. And if you did everything correctly, then you should obtain this number. Okay. 0.02897. I'll put that for now, because this is not the final answer. The final answer, well, we found the error term, and what we do with the error term is we add it and subtract it to the point estimate, and that gives us our confidence interval. That will give us the confidence interval. So the lower bound is the point estimate minus the error, 0.7818 minus 0.02897. The upper bound is, well, the addition. That's why the error term is so important. That's pretty much all of the work. 0.7818 minus 0.02897. Same thing, but with a plus sign. But it only wants 3 decimal places. So say 0.753, 0.811. 0.753, 811. Okay. Suppose let's keep going. So they're talking about point estimates. I still see the p-hat notation. So that tells me we're still in the same section on talking about, well, not only point estimates, but proportions. So remember, with point estimates, x over n, out of 1,014 people that are surveyed, 536 resemble a certain characteristic. The first part's pretty easy. It's just the ratio of that, or the proportion. 536 divided by 1,014. And they want 3 decimal places, so I'll just go ahead and type that in. 3 decimal places, 0.529. This is worrying about the requirements, which on the test, I'm not really going to ask about 2 of these too much. We're going to assume that this is a simple random sample. That's one of the conditions. The sample size can be assumed to be less than or equal to the population size. So those 2, again, don't worry about those. What we worry about is the condition of, so what we really want to check in this situation is NP1 minus P is greater than or equal to 10. That's primarily what we're concerned with. Because what this tells us, well, with the hats too, because what this tells us is, are we allowed to assume normality? And we need to check that and check and see if it's greater than or equal to 10. And we know what n is, 1,014. P hat, we just figured out, is 0.529. 1 minus 0.529. One zero one four times 0.529. 1 minus 0.529. We definitely get a number that is larger than 10. They want 3 decimal places, 647. .647. That's the important condition to check, because that's the one that primarily gives us normality. The other ones are just other, I guess, less important requirements. Once we get this assumed normality, you can go ahead and construct and interpret a 95% confidence interval for this. And so anytime we construct a confidence interval, that means we yet again need to use the formula that we talked about before, which means we need the point estimate plus or minus the error. We need to figure out the error term. And so the error is going to be 1 minus alpha over 2 for a 95% confidence interval. The complement of 95% is 5%. That's why I have 0.05 here. Again, the complement of 95 is just the remaining 5%, but we need to convert that to a proportion. And then this is the square root of p hat. We said p hat was 0.529. 1 minus 0.529 divided by n, which was 1014. So from here, minus 0.05 divided by 2, square root of 0.529 times 1 minus 0.529 divided by 1014. They ultimately want 3 decimal places. 0.031. But this is not the answer. This is not the final answer, because we need a confidence interval. And all we found was the increment size. Basically, how do we go from the point estimate to the lower and the upper bounds? And I'll put that up here. Lower bound is the point estimate minus the error. The point estimate was 0.529. The error we just found to be 0.031. And then I'll do the upper bound up here, which is simply a plus sign. 0.529 plus 0.031. 529 minus 0.031. 529 plus 0.031. 498.56 are the lower and upper bounds, respectively. So 95% confident that this is between 0.498 and 0.56. Actually, I think in terms of the statement, I think it should be part B, which the only difference is there is a 95% probability. So I think technically the wording's that way, but again, what's more important here, again, I'm not going to nitpick on that during the test. As long as you can make the association between, well, ultimately figure out these numbers. That's what I care about, that you can actually figure out these numbers. And because we get this interval between 0.498 and 0.56, then they ask, well, what about 60%? Would you expect 60% to be a proportion that comes up? Well, our interval that we just figured out in the previous part is between, well, 0.498, which is 49.8%, and 56%. So 60%, which is what they're asking about, is not in that interval. That doesn't mean that it can't happen, because we said that there's a 95% chance that something occurs between this interval, which means that there's a 5% chance that something doesn't occur in that interval. So it's possible, but it's not likely. And I know we did a problem about the supermajority before, and this is because the interval does not contain ultimately 0.6 or 60%. It's just interpreting what this result's telling us. Here, they want us to find the 95% confidence interval, the lower and upper bounds, which already seems like we have that. Actually, they changed the wording here. These are the people who believe that televisions are a necessity. And then what we found was people who believe that televisions are not a necessity. So actually, they want the opposite of what we found. They want the opposite of what we found. And so how we do this, and we did a problem like this on one of the, in class, I can't remember what example offhand. Example 4 on page 81, we did this in part D. And so what we had to do, since they were looking for the complement idea, then we had to complement the lower and upper bounds from before. Notice I have them on the top of the screen here. The lower bound, we complement the lower bound to get the new upper bound. And we complement the upper bound to get the new lower bound. And we have to switch them because the sizes end up switching when you complement. So 1 minus 0.56, that's probably 0.44, I'd imagine. 0.56. Is that 0.502? 0.8. 0.44, 0.502. So that's a pretty typical population proportion example. Okay, let's keep going. And so this is one more problem that pertains to determining the number of samples you would need. So this was, the formula is based off of page 82, where it's basically the formula we had before, but algebraically rewritten. And there's two formulas here based off of if you are given a population or a point estimate versus if you're not given one, and you're just kind of estimating. So in part A here, they give us a prior estimate. So for part A, we can use this formula. P hat, 1 minus P hat, E squared. So this assumes that we have a few givens here. Now they gave us the proportion in the statement of part A. It was 0.36, 1 minus 0.36. And then this Z with the alpha divided by 2. Well, we said that that is the inverse norm in the calculator. This is 1 minus alpha over 2, something over 2. Now alpha, they told us that we have a 95% confidence, level of confidence. This is 1 minus 0.95, which is 0.05. This is 0.05 divided by 2. And this divided by the error, they said that they want the estimate to be within 0.04. So 0.04 tells us the error as well. We still have to square all of that. Now, if we plug this into the calculator, 0.26, 1 minus 0.26. I want to open up a new parenthesis before I go find the inverse norm, because I still have to square everything at the end. So I just opened up a parenthesis before I touched inverse norm. Now let me go find inverse norm. Your area will end up being 1 minus 0.05 divided by 2. That will be your area. Again, make sure your mean is 0 and your standard deviation is 1. Your calculator might look differently, but they close your parenthesis for you. And then from there, you can proceed with divided by 0.04. Close that parenthesis so that you can square everything at the end, because there is a square. Type that in correctly. Hopefully I typed in everything correctly. 553 point. They went to the nearest integer, which makes sense. They want us to also round up to the nearest integer, because we're talking about samples, talking about people. This is going to be 554. They're forcing us to round up no matter what. Part B, I guess I'll do part B up here. Part B, they say, well, let's just assume that there was not a point estimate given, which means we're using the second formula right here. The 0.25, but everything else stays the same. So N is now 0.25, and everything else is going to stay the same. So notice it's almost the same formula. It's just the first part of it. The first part of the formula has a 0.25 instead of 0.36 times 1 minus 0.36. By typing that in very similarly, it forces us yet again to round up, so that's 601. So notice, because we don't have a prior estimate, they want us to be more safe about this, and we have more people that we're required to interview as a result. So let's go ahead and try one more example here. One or two examples. So this is the only time when dealing with t-values when we need to use the table in the back of the notes. The t-distribution, it's on the very last page of the appendix. Now, this is asking, well, what about if we're trying to find the t-value where the area to the right is 0.1 with 23 degrees of freedom? So this problem is basically making sure you know how to use the table. So if we scroll all the way down, again, this table is going to be given on your test. This is the t-distribution table. Let me just write everything down. So the area to the right is 0.10, 23 degrees of freedom. We need both of those pieces of information here. So the area is 0.10, which would tell us that we're looking at this column. And 23 degrees of freedom would be this row right here. So it tells us that the t-value is 1.319. So that's how you read this, 1.319. And we can do the same thing with the next part. Area to the right is 0.005 with 13 degrees of freedom. .005 with 13 degrees of freedom. This is 3.012. Now, all of these pertain to areas to the right. So when they ask for area to the left, basically it's the same thing, but because we are negating the way in which we're looking at this, so we can see from the diagram, this all pertains to area in the right. So whenever we look at area to the left or the left tail, we simply need to do exactly the same thing as if it were to the right and then negate the answer. So throw a negative sign in front. So here, 0.05 with 7 degrees of freedom. 0.05 with 7 degrees of freedom. There's 0.05. Here's 7. So normally we would get 1.895, but because this is area to the left, we need to provide the negative. So negative 1.895. And so finally, the last one I'll do before I wrap up here, the critical t-value that corresponds to 60% confidence. This means we need to find alpha here. Or actually alpha divided by 2. Alpha refers to 40%. So really what it's asking for is to find the t-value, or 0.2, with 20 degrees of freedom. .2 with 20 degrees of freedom. 0.86. So I am out of time. So that concludes this last day of class. The exam, as I mentioned, will be on Thursday at 8 a.m. in this classroom. Everyone is required to show up. Besides for that, that's all I have. See you all on Thursday.